What a wreck!
Yeah, this plane looks just as bad as some of the cars we've been in.
Hi, I'm Vince.
And I'm Larry. We're the crash test dummies for the National Highway Traffic Safety Administration.
Larry and I have done more than 10,000 crash tests in order to help protect motor vehicle passengers like you from serious injury.
On this episode of NASA Connect, you'll learn how measurement ratios and graphs are used by NASA engineers every day as they conduct some pretty extreme tests.
You're telling me? NASA Langley uses crash test dummies like us to help them improve the crashworthiness of aircraft. Like we always say, take it from a dummy.
Make sure you buckle up. So stay tuned as Van and Jennifer show you how NASA tests aircraft to the extreme. 3, 2, 1, crash!
You know, skidding tires is just one way that NASA Langley Research Center conducts tests to improve aircraft performance and safety.
Hey, welcome to NASA Connect, the show that connects you to the world of mathematics, science, technology, and NASA. I'm Van Hughes.
And I'm Jennifer Pulley, and we're your hosts, along with Norbert. Every time Norbert appears, have your cue cards from the lesson guide and your brain ready to answer the questions he gives you. And teachers, every time Norbert appears with a remote, that's your cue to pause the videotape and discuss the cue card questions he gives you.
This show is oozing with math. We'll see how NASA researchers measure and collect data, develop ratios and graphs to analyze their data, compare the results, and then predict possible solutions for their real-world problems.
Using these math concepts, students like you will conduct an experiment very similar to NASA research that you can try in your classroom. It's a blast.
Then, grab a computer and a mouse and log on to the web. Our NASA headquarters correspondent, Dr. Shelley Canwright, will get you connected to our web activity.
Today, we're at NASA Langley Research Center in Hampton, Virginia. NASA Langley is the oldest of the 9 NASA facilities.
Here's another Langley fact. See this huge structure? Its original name was the Lunar Landing Research Facility, but today we call it the gantry. In the 1960s, Apollo astronauts trained right here at NASA Langley to land on the moon.
The title of today's show is Measurement, Ratios, and Graphing. 3, 2, 1, crash. And get this, measurement, ratios, and graphs are used every day by NASA researchers. They make predictions and draw conclusions using the data they collect from their research and extreme tests. Speaking of graphs, does this look familiar? Of course, this grid would never fit on your desk. It's huge! Each square measures 1 meter by 1 meter. Anyway, NASA researchers use this grid for film analysis.
The aircraft passes in front of the grid and is tracked by a camera. Then engineers can measure the distance the aircraft travels in a certain amount of time. NASA engineers analyze this data and make conclusions based on the test results. Finally, they communicate what they've learned to aircraft companies so they can build safer aircraft. We'll learn more about how NASA crashes aircraft from this gantry later on in the show.
Right, but first, let's learn more about NASA Langley.
Today's National Aeronautics and Space Administration, or NASA, was established in 1958, but its historical roots reach back much farther to the early 1900s. Powered flight was developed by the Wright brothers in 1903. However, during World War I, America realized how far it was behind other countries in developing air power. So, Congress created the NACA, or the National Advisory Committee for Aeronautics.
What is aeronautics?
Aeronautics is simply the science of flight. Anyway, the NACA decided to build an aeronautical research facility, and they found the perfect location. A site was chosen in Hampton, Virginia, and the facility was named the Langley Memorial Aeronautical Laboratory, after an early aviation pioneer, Samuel Pierpont Langley.
Later, in 1958, Congress changed the name of the NACA to NASA, and NASA Langley Research Center helped give birth to the space program. America's first manned in space program, Project Mercury, began at NASA Langley.
Today, NASA has grown to 9 centers across the United States that are involved in aeronautics, earth science, space science, and human exploration of space. The knowledge gained from NASA research can be found in everyday objects like sunglasses, athletic shoes, cordless products, and even the highways we drive on.
So, the next time you fly in an airplane, remember that almost every American aircraft today uses technology that was developed right here at NASA Langley Research Center.
Okay, now that you've gotten some facts on NASA and NASA Langley, let's see what type of extreme tests NASA Langley conducts at the Aircraft Landing Dynamics Facility.
The what?
The Aircraft Landing Dynamics Facility. But that's a mouthful, so they call it ALDF, or ALDF for short. Let's find out how NASA engineers are using math, science, and technology to solve the problems they're faced with every day.
How is the test set up to solve the problem?
How are graphs used to find possible solutions?
What visual method did NASA engineers use to represent their solution?
The ALDF allows NASA Langley to test tires, wheels, and brakes of vehicles like airplanes, cars, trucks, even the Space Shuttle orbiter, and makes them safer for everyone. For example, because jet airplanes and the Space Shuttle land at really high speeds, we have to simulate those speeds here at the ALDF if we want our test to be accurate. This is done with the use of pressurized water, a carriage, and the tire or gear being tested. 10,000 gallons of water push the carriage down a track. When the desired speed is reached, the tire is lowered onto the test surface. Instruments are used to measure the forces acting between the tires and the test surface. These data are collected by a computer and made into a graph. By comparing many graphs, we are able to predict how a tire might behave under conditions other than what we test. Some of the many tests we've conducted at the ALDF include something known as hydroplaning. That's when you drive your car or land an airplane too fast on a water-covered road or runway, and you actually start skiing on the water. That's fun if you're boating, but not very fun if you're in an airplane. So the engineers at the ALDF figured out that putting grooves in the runway gives the water a way to get out of the tire footprint to keep you from hydroplaning. This idea found its way to the highways you and your family drive on to keep you safe in the rain.
Wow, so NASA Langley engineers have solved lots of real-world problems.
That's right, but remember the ALDF only simulates tire wear, landing speed, and runway surfaces. Sometimes in order to solve real-world problems, you have to go to where the problem really exists. Take Kennedy Space Center in Florida, for example. This is the #1 landing site for Space Shuttle launches and landings, and the conditions have to be just right for the Space Shuttle orbiter to take off or land.
Conditions? Like the weather?
Well, that's part of it. If conditions like the runway texture and the winds aren't just right, the Space Shuttle tires will wear out and could fail. You see, the runway at Kennedy Space Center was built very, very rough, so the water would drain off of it, and it wouldn't be too slippery when it was wet. We didn't want the orbiter to hydroplane. But because the orbiter tires land with the weight of about 150 cars and as fast as 250 miles per hour, the rough runway was like a cheese grater on the tires. Too much wear could cause the tires to fail during a landing, and we want to prevent that. Tire wear gets even worse when the orbiter lands in a crosswind.
Hey, I've heard that term before. But what exactly is a crosswind?
Well, a crosswind is the wind blowing at an angle across the path of an aircraft. Landing in a crosswind actually causes all of your tires to roll slightly sideways. We call that a yaw angle. And just a small amount of yaw angle can cause a tremendous amount of tire wear. This tire wear limits the amount of crosswind the shuttle can land or launch in, which causes delays. NASA wanted to double the crosswind limit that the shuttle could launch or land in safely. Our job was to find out how to smooth the rough runway surface to reduce tire wear without making it too slippery when it was wet.
So, Bob, I guess you used the ALDF to figure out which runway surface to use at Kennedy.
That's right, we started right here. But because the test track here at the ALDF is only a half-mile long and the runway at Kennedy is 3 miles long, we really couldn't take a bunch of short-distance runs here and add them together and accurately predict the wear for a whole shuttle landing. We needed a full-scale test. Somehow, we had to make the shuttle tire think it was on the real shuttle.
Well, how did you do that then, without using the real shuttle?
Well, some very smart people at NASA Dryden Flight Research Facility in Edwards, California, came up with the Convair 990 program. This took the idea of the ALDEF one big step forward and allowed us to land an orbiter tire on whatever runway we want, all at full scale. A large fixture was built in the belly of the airplane that could apply the correct weight to a shuttle tire while the pilots landed the airplane at about 250 miles per hour.
Okay, so the Convair 990 could simulate a shuttle tire landing pretty well, but how did you figure out the best runway surface?
Well, that's a good question. Before we put the Convair 990 to the test, we had to get an idea of what kind of runway texture might or might not reduce tire wear. Building lots of 3-mile-long test strips would be very expensive, so we conducted a sub or small-scale test using a test vehicle from Langley. This truck allowed us to wear out smaller airplane tires by rolling and yawing them on lots of different textures, and it allowed us to predict which surfaces might be worthwhile to install in 3-mile-long test strips.
How do you measure tire wear?
Well, after rolling these smaller tires a certain distance, we would weigh them and see how much rubber was worn off. Then we graphed that lost weight with distance. This graph shows tire wear for some of the different surfaces we tested. We tested 18 different textures in all. On the graph, we put a line showing the maximum amount of wear that we could live with to reach our new crosswind limit. Any surface that showed wear higher than that limit would be out of the question, and you can see that limits our choices.
Cool. So now you had 5 runway surfaces instead of 18. What's next?
Next, we conducted friction tests on the surfaces when they were wet to see how slippery they might get in the rain. This graph shows the results of those tests. We also put a line on this graph showing the minimum friction level that we could live with. A surface with less friction would make it too hard to steer or stop the shuttle if the surface were wet. This also limits our choices, and when we combine these two graphs, it said that we could only predict that 3 of the original 18 surface ideas would both reduce wear but not be too slippery. With our top 3 choices, we built 3 test strips and landed the Convair 990 on each of them. Comparing graphs and making predictions really helped us to narrow down our selection of expensive test strips.
Okay, so how did you collect data from the Convair 990?
Well, during our tests, we measured the tire forces with sensitive instruments, and then we used a computer to graph the results. We also combined video footage of each test to find out when each of the tire's cord layers were worn through by counting them. Finally, we could graph the forces and the tire wear and compare the performance of the new surface with the rough surface. This graph showed that we got less tire wear for the same forces on the new surface, just like we predicted. Using all these test results, NASA shuttle managers now had the information they needed to decide to change the texture of the entire runway surface at Kennedy Space Center. That's almost the equivalent of 100 football fields. Today, the shuttle orbiter has the ability to withstand twice the amount of crosswind without worrying about tire wear, and we use measurement, graphs, and predictions to do it.
NASA Connect traveled northwest to Richmond, Virginia to conduct the student activity for today's program.
Hi, we're at Chandler Middle School in Richmond, Virginia.
NASA Connect asks us to help you understand how to do this show's student activity.
Earlier, we learned that NASA Langley's Aircraft Landing Dynamics Facility, or ALDEF, uses a carriage, pressurized water, and a test track to test tires. Let's simulate the research they do at ALDEF using the Effervescent Non-Combustible Dragster, or ENCD. You'll test different ratios of water and effervescent tablets to propel the dragster down a track. Then you'll measure the distance your dragster travels and create graphs to analyze the results, just like NASA researchers do. The instructions for the entire student activity are found in the educator's lesson guide, so make sure your teacher has it. Before we can test our dragster, we need to prepare 3 things: the dragster, the propulsion device, and the test track. First, let's make the dragster. The materials you need, like milk tops and straws, are easy to find. After you've made the dragster, it's time to assemble the propulsion device. This is made by using a shoebox. Finally, prepare the test track, kind of like the one at ALDEF. This next step is very important for making accurate measurements. Now you're ready to begin testing your dragster. Make sure you have your safety goggles on. Place your dragster behind the starting line and slide the skewer on the shoebox into the straw on the dragster. Make sure you line up the dragster so that the front wheels are on 0. Place your foot into the shoebox to hold it in place during the test. Let's conduct the trials. To propel our dragster down the track, we'll use a ratio of an effervescent tablet to water. For the first trial, use the ratio of half a tablet of fuel to 2 teaspoons of water. Fill the film canister with the water and hold it near the front of the shoebox. Quickly drop the fuel tablet into the canister, snap on the lid, attach the canister to the shoebox, and stand back. Measure the distance your dragster traveled and record that distance on the data sheet. After every trial, rinse the film canister with clean water and dry it with a paper towel. Now, repeat the trial using the same ratio of water to fuel and record the distance traveled. Average the distance traveled for the 2 trials. Remember how NASA engineers used prediction to determine which runway was best for the space shuttle? Let's do the same. Look at your first trial and predict what size tablet might propel your dragster a greater distance. After you choose a different size tablet, run 2 trials with the new ratio. Be sure to use the same amount of water. Average the results like you did before and record on the data sheet. Based on your findings, predict another size tablet that might propel your dragster an even greater distance. Run 2 trials on the new ratio and average the distance. After you've completed all your trials, your teacher will get you started on graphing your data, then help you understand how to analyze the results.
Now, how can we display the data that we collected? Think about the information that we collected and how we are going to compare it on the chart. Now that we have our graph displayed, I would like a member from each of the groups to come up and to plot the average of their trial run on the chart. Now that we've finished and we've collected all of our data, it is now time to analyze it. What type of graph is it? Is it a bar graph? Is it a line graph? Or is it a scatter plot? What was the maximum distance our dragster traveled? What tablet ratio produced the greatest distance? Do you think there is another tablet ratio that could produce an even greater distance? Okay, how can we find it out?
Let's test it.
NASA Connect would like to thank the Hampton Road section of the AIAA for their help with the classroom activity.
Hey teachers, if your students want to conduct this awesome activity, then visit the NASA Connect website and download the lesson guide for this program. And kids, make sure you visit our site too. There are lots of exciting activities for you to check out. Speaking of the web, NASA Connect travels south to Norfolk, Virginia for today's web-based activity.
Hi, Norbert and I are here at Nauticus in Norfolk, Virginia. This maritime center is huge and features over 150 interactive exhibits. Nauticus and NASA are teaming up for this program of NASA Connect to introduce you to the show's online activity, the NASA EduTour. But first, with a little help from Norbert, let's take a quick tour of Norbert's online laboratory and observe the type of lab features that are just a mouse click away to support the NASA Connect programs. The digital content found in the lab makes a vast collection of information, ideas, resources, and experts accessible to you at any time. Okay, everybody, well, as you can see, we are here now inside Nauticus, where some students from the Chrome Club have gathered to introduce you to the NASA EduTour, a digital tour of the NASA Langley Aircraft Landing Dynamics facility. Now, this digital tour has been designed to augment the video presentation and to provide you, the user, the opportunity to use this information in ways like NASA scientists. So, let's take a sneak peek at the tour.
From the NASA Connect website, go to Norbert's lab, where you'll find a button that gets you to the ALDF EduTour. There are 4 main parts that make up this NASA lab: propulsion, test carriage, track, and arrestment system. When you start the tour, you'll get information about how the propulsion system works, and also the science behind the system. Once you understand that, you'll do an activity that helps you visualize the mathematics and science concepts. You'll play some animations, then answer questions about what you've observed. There's an activity for each one of the 4 parts and related questions that will test your knowledge. But we want you to see the website for yourself, so that's all we'll show you now. Oh, by the way, there is a review at the end of the tour that will summarize what you've learned during your visit to the lab.
A special thanks to our university student mentors from the AIAA Hampton Roads Student Branch. The AIAA, as a special Connect partner, offers its students as mentors to registered Connect classrooms. To learn more about the mentoring program, check out our website. Bringing to you the power of digital learning, I'm Shelley Canright for NASA Connect Online.
So you see, using the ALDEF, Langley's test truck, and the Convair 990 to test tires and tire wear really helped engineers solve their problem with the shuttle runway at Kennedy Space Center.
Right. They run tests, measure and collect data, graph the results,
and predict solutions to their problems. Sounds similar to what you do in your classroom?
Does NASA Langley conduct any other extreme tests?
Funny you should ask. Remember the title of today's program? Measurement, ratios, and graphing? 3, 2, 1, crash? Well, NASA Langley actually crashes aircraft to test them for safety, right here at the Impact Dynamics Research Facility.
How is technology used to collect the mathematical data in crash tests?
Why is area important in the results of the test?
How are ratios used to find a solution?
The Impact Dynamics Research Facility is used to conduct full-scale crash tests of aircraft. The aircraft to be tested suspended from the gantry, pulled back to a calculated release height, and then released to swing like a pendulum into the impact surface below. Just before crashing, the swing cables are released and the aircraft goes into free flight. The cables attached to the aircraft are released by pyrotechnics or explosions. It's pretty cool to watch. We crash aircraft so we can see how safe they are and develop ways to make them safer. IDRF is very similar to what the auto industry does with cars. Everyone has seen the commercials with cars being crashed into barriers and the crash dummies responding to the forces. Our crash test dummies are wired with sensors and data are collected to determine the crashworthiness of an aircraft. Crashworthiness is how well an aircraft protects passengers in the event of a crash. We use the data from the dummies to make improvements to aircraft designs for crashworthiness.
Lisa, that is just so cool. I mean, you get to crash things for a living.
and we get safer aircraft.
You're right, Dan. The testing and the research conducted at the IDRF can really benefit all airplane passengers. One of our main goals is to reduce the force on airplane passengers during a crash. We want to create structures and materials that dissipate or absorb the energy from a crash before the energy gets to the passengers. Take a car, for instance. Structures like the bumper and frame are designed to crush. When these parts crush, they dissipate or absorb some of the energy so that the passengers are less likely to be injured.
Lisa, we all know that planes don't have bumpers.
Right. However, there are parts of an aircraft that can absorb energy in a crash. Parts like the subfloor, which is the area under the floor, the landing gear, the seat, and even the cushion can absorb energy. Restraints, like the seat belts, are also necessary to keep the passengers from flying through the aircraft during the crash. When these parts and structures are designed correctly or optimized, the passengers have a better chance of surviving a crash.
But Lisa, how do you design aircraft parts to absorb energy?
Good question. We use human tolerance data and crash test dummy data to develop better energy absorbing designs. You see, aircraft are made of different materials. Some are made of metals like aluminum, and some are made of composite materials like graphite or fiberglass. A tennis racket is a good example of a graphite material, and most small boats are made of fiberglass. Metals and composites perform very differently in a crash, so we have to design the parts to complement the materials the aircraft is made of. Basically, we would not design a subfloor in a composite aircraft the same way we would design a subfloor in a metal aircraft.
Can you really design a subfloor that absorbs energy?
Yes, in 1994 we tested a graphite aircraft called the Lear fan. When the original aircraft was released from the gantry, it was extremely rigid and nothing crushed. According to the crash test dummy data we collected, only one of the 6 passengers survived. So we used that data to design a new energy-absorbing or crushable subfloor. It would be like putting a bumper under the floor. Then we built and tested small sections of different subfloor designs until we had the best design. A second Lear fan was modified by installing the newly designed subfloor and tested. The results showed that the new subfloor improved the Lear fan's crashworthiness by reducing the forces on the passengers.
Oh wow, this looks crazy. How do you collect the data from the crash tests?
We use a digital data collection system that's designed to handle the impacts of a crash, not like this one. All the instruments on board are wired to the data collection system, and after the test, The data are downloaded onto a laptop computer to be analyzed by the researchers.
In school, we analyze data and we make graphs. Is that what you do?
Absolutely. We make graphs of the data collected and compare those to other graphs. This graph from an actual test conducted here at IDRF shows the ratio of g-force to time. You can feel the sensation of g-forces when you ride on a roller coaster. It's what you feel pushing you into your seat on a loop. As you can see, our graph has a curve shape. Next, we calculated the area under the curve and compared it to a human tolerance graph. This graph shows the maximum energy or g-force a human can tolerate over a specific time. The plot goes from 0g to 50g and back to 0g in a very short amount of time. The shaded area within the triangle is the amount of energy a human can tolerate in 100 milliseconds. Next, we set up a ratio. By comparing the shaded area under the dummy data to the shaded area under the human tolerance data, we can determine if the passengers survive. We want this ratio to be less than or equal to 1 if passengers are to survive.
Okay, Lisa, I have one more question for you. How does all the information that you collect here help aircraft safety?
By using measurements and graphs, we present the data collected from tests at the IDRF to the aircraft companies and to the FAA or the Federal Aviation Administration. Then the aircraft companies can use the new designs of their aircraft. The FAA may use the information to establish new rules and regulations for aircraft safety.
Well, that about wraps up this episode of NASA Connect.
It sure does. And, Van and I would like to thank everyone who helped make this program possible. We hope you've all made the connection between the research and extreme tests conducted at NASA Langley and the math, science, technology you do in your classroom every day.
Jennifer and I would like to hear from you with your questions, comments, or suggestions. So write us at NASA Connect, NASA Langley Research Center, Mail Stop 400, Hampton, Virginia, 23681, or email us at connect@edu.larc.nasa.gov.
Hey teachers, if you would like a videotape of this program and the accompanying lesson guide, check out the NASA Connect website. From our site, you can link to CORE, the NASA Central Operation of Resources for Educators, or link to SpaceLink and locate your local NASA Educator Resource Center. Until next time, stay connected to
mathematics,
science,
technology,
and NASA.
See you then.
Hey,
Nice
how you
there.
doing?
How you doing?
Really enjoyed working with you.
Yeah, sure.
Okay, and action.
All right.
So, how many crashes you been through?
About 1,500.
Skidding tires is just one way that NASA Langley Research Center conducts tests to improve aircraft.
Get pumped up there. Get pumped up. All right, ready? There you go. Here we go.
It's part on there. Part of that
Digital data collection system.
Jennifer and I would like to hear from you with your comments, questions, or suggestions. So... Oh!
Got him!
Oh! I can hear the blood squeezing out.
Oh.